Thanks for coming. Today I'm going to talk about SmyteDB, which is a framework that we open sourced recently to build distributed databases with Kafka and RocksDB. And a core requirement here that we want to operate our database systems as cheaply as possible, because as an early stage startup, we want to reduce our costs as much as possible. So before we get to the database part, what is Smyte? So we're an early stage startup that's trying to build a trust and safety platform for the internet. And more specifically, we want to build tools to help our customers to fight against online fraud, spam, scam, harassment, all kind of bad activities on the internet. And here's just a partial list of great customers that we are proudly serving. So this is how Smyte works. This looks complicated, but I promise that the rest of the talk will be much simpler. So the key idea here is that our customers send us data using our public REST APIs or our client SDKs, etc. We get this data and put it into our system, and using a large number of classified workers, or we call action processors, to go through the data and generate a verdict for each of the actions that we receive to tell our customers whether something is bad or not. And in order to do that, there's a large fleet of databases that the action classifier has to consult and read during the process. And at the end of the process, it will accumulate a set of updates to the database. But instead of writing those updates to the database directly, it will send a bunch of Kafka messages to the cluster. Then the Kafka messages will in turn be consumed and applied to the corresponding databases. And in the rest of this talk, I'm going to explain how we do that and why. So let's look at this bottom half of the graph. There are a lot of databases here. So what are they? It's really just a set of databases that store the signals for our data classification. For example, we have a lot of counters. We calculate quantiles. We store a list of labels for all the customers, and we do similarity search, etc. And let me give you a very concrete example. For example, we often ask questions like, how much activities have been seen on a given IP? Or more specifically, for the given IP, how many requests we have seen in the last hour, or how many signups we've seen on this IP in the last hour. Or another example would be, given a pair of IP and an email domain, how many signups have we seen in the last hour? And if the number is very large, then that's a strong indication that something bad might have happened for that pair of IP and email domain. Another example would be that if a large number of similar texts have been posted by the same actor in the last hour, then that's another strong indication that something bad has happened. So that's these are a few examples of the counters database that we build. Another example would be a label database. For example, given a username or email domain, what other labels have we applied to it before? For example, a username might be a young actor, which means we have seen this user before, but not long ago. Another example would be that this user came from a known bad ISP, or last time this user logged into our system was from a very faraway location than this time. These are all labels that we can use to classify new actions in the future. And compared to the counter database, this is a list database where you want to give input as a username, a single key, and you get a list of output instead of a single output. Now, these are just a few examples of databases that we run, and we want to build a whole fleet of them to store all kinds of different signals for our data classification. And we want all these nice properties about databases, such as being sharded, accurate, durable, replicated, and fault-tolerant. But as an early stage startup, the most important property here for us is cheap. We want to run it as cheaply as possible. And in order to do that, I'll go through a set of techniques that we apply in order to achieve that goal. So the first version that we used when we first started is just like a lot of other early stage startups. We start with Redis and MySQL because why not? We we have a very good hosted SQL solution in the cloud. For example, we use it in Google Cloud. So we can run MySQL cluster without really having a DBA team. That's how we get started. It's pretty easy to run when you don't have that much data. Unfortunately, it is not a cheap solution. Well, storing in memory in Redis is inherently expensive, and also a hosted SQL service is very easy to operate, but compared to plain VMs in terms of unit cost for CPU and memory, it's actually quite expensive. And in the case of Google Cloud, it's about twice as expensive. So we want to, as we grow, we want to find a solution that is going to be much cheaper than this. And so far, in this first version of our database, we can achieve sharded database. We can be atomic. We can be replicated, but it's not really durable in the case of Redis. And it's not very cheap to run, as I have explained. And it can be fault tolerant, but takes some effort to do so. Now, let's look at this next version that we built. So in order to solve the first problem, durability, we added Kafka to the equation. And the reason why we do that is Kafka is just really a durable sequential log of messages. So as I explained earlier in the presentation, instead of writing to the databases directly, we can accumulate the writes and generate a set of Kafka messages that will be sent to the Kafka cluster at the end of the process. And the reason why we do that is because unlike an online e-commerce service or social network, having some extra latency to our writes are not the end of the world. So, but because of that, we can afford accumulating the updates instead of writing directly to a database in real time. And at the end of the process, we can update the database by applying those Kafka messages to the database so that we can achieve very scalable writes while having, only having some mild increase in the latency in terms of writes. Another question that came up is that now Kafka itself is durable, but we're not keeping all the data at all time because Kafka has a retention problem. Typically, people do 7 days, sometimes do even like 1 or 2 days. To solve this problem, we have another open source project that on our GitHub repo that helps to upload all the old Kafka messages to places like S3 or Google Cloud Storage so that if you want to go back in history, you can simply download those messages that will be ordered the same way that normal Kafka messages would in terms of Kafka offsets and apply them back to a database to get all the data that has been expired in the main Kafka cluster. So now, in the second version, we solve a durability problem. If we lose some data on our database node, that's no problem, because we can get the data back by just reading either from the Kafka cluster directly or by downloading all the messages that we have uploaded to S3. Now, we want to make it cheap. And the way we do that is to replace our storage engine with RocksDB. And the reason why we chose RocksDB are mostly for 2 reasons. One, RocksDB is very simple, but it's very powerful and tunable. And we'll get into details later. And secondly, its on-disk structure is really, really simple. It's just a list of SST files and a manifest that shows how do we read the data back. And that will help us to make things much easier to operate and much cheaper. So about optimization, there are a lot of interesting things that we can do with RocksDB that helps us building different databases for different purposes. For example, if we want to build a counter database, it's mostly point lookup. So we can do point lookup optimization with RocksDB. And if we want to get a list of labels for a user for an IP, then we can do prefix scanning with RocksDB, both of which are natively supported. And also, there are advanced features like compaction filter, which we use a lot in order to expire old data on database. And if we want to do atomic write after read, then you can apply a merge operator to your database. Now we have this very nice tunable database, but it's really just a library that writes data to disks. How do we turn that into a distributed database? Well, since we already have Kafka, we have solved the durability problem. If we lose some data on RocksDB, we can get data back by reading from Kafka. And also, Kafka itself is replicated if you do it right. So later, I'll talk about how do we replicate our database using Kafka. And at the end, all we need to do is write a server program that serves data to the client by reading and using Kafka APIs. Now, at this point, we have a simple solution that do writes through Kafka and read directly from RocksDB using a server written in C++. But it's so much cheaper than what it was before, because now all data goes to disk, and we chose to use a cloud persistent disk. I think it's called EBS on Amazon, but really the same thing. The key idea here that instead of writing to a local disk, by writing to a cloud persistent disk, we can easily operate our database. If a node of VM dies, then we can move the unmounted disk, which might happen automatically, then mount a disk somewhere else, and so that we don't have to recover data by reading from Kafka from scratch. Another important property to this is that at least in Google Cloud, persistent disk is actually cheaper than local SSDs. Additionally, when we first started, we may not have that much data for a new database, and we don't have to allocate lots of storage to it. Let's say we start off with only 100 gigabytes. Later, if we reach a certain threshold, say 80%, we can go to the node that has a disk mounted and do an online disk resize, which will allow us to have a much larger disk without paying the cost up front. And because it's online disk resize, we don't have to interrupt the running database or to restart the process or anything. It just happens automatically. In addition, RocksDB allows us to split the data into different disks for the same database, so that if SSD gets really expensive, we can allow certain data that is usually the old data to be stored in a cheaper non-SSD storage, and the newer data on the more expensive but faster SSD, which further reduce the cost. And the last point here is that now, since we're writing and running our own databases instead of renting a hosted SQL service, we only pay for the unit CPU and memory units that we need, which, as I mentioned earlier, is about half the price of that for a hosted SQL service. Now, at this point, we have achieved most of the nice properties, but since we're not using MySQL anymore, we don't have the support for a master-slave setup that we get for free from cloud services, so we need to find a way to make it replicated and fault-tolerant. And the final piece of our puzzle is Kubernetes. So Kubernetes is a service that allows to run replicated containers in the cloud. In the case of distributed database, it doesn't have to use Kubernetes per se, but since we're building our system in Google Cloud, it seems natural to use Kubernetes because there's a hosted service that we can use directly. And the way we use it is really simple. Instead of having one set of RocksDB services, each partition that we have, we will run multiple copies of it. And Kubernetes will help us to ensure that we have a certain number of copies for each partition. It's really easy to set up, in this case, a new replica. If we want something new, a new replica can be created by just starting from a recent backup, which is a snapshot of your cloud disk. And then, because the disk itself contains offsets from which the last Kafka consumer stopped, we can resume the Kafka consumption from that point and start writing new data to the disk. which usually happen very fast. And as soon as that reaches 0 lag, we claim that replica is ready and we can serve read traffic. And interestingly, we did some simple benchmark. And in one case, we have sustained about several, I think tens of thousands of writes per second for one database replica. And if we run a sharded database at our scale, achieving millions of writes per second is actually pretty easy. So finally, an important property of this setup is that the replicas are actually independent of each other. They don't have to be aware that there are other replicas for the same database partition. As long as they have access to Kafka, as long as we know how to scale Kafka. Unfortunately, there's not a lot of tools available and public knowledge about the best practices of scaling Kafka. And in the case of LinkedIn, we know that we can scale Kafka to a very large extent. Now that you have multiple copies of the same database, we want to make sure that client can talk to them and they're well balanced. The way we do that is to use a construct from Kubernetes called cluster IP, which runs a daemon process on every host where we run the clients. And the daemon process would read the cluster and find out what are the available ready replicas and update the local IP table for the clients. And the clients only need to talk to the special cluster IP, which is a virtual IP. And then the local IP tables would ensure that all the accesses would be well balanced across all the replicas. Now, finally, we have this nice set of properties that we can we want for our distributed databases, and more importantly, it's very cheap. But you may ask, is it going to be very expensive to run multiple copies? An interesting trick that we use is that at least in Google Cloud, there's a special type of VM called preemptible VMs, which is about a third of the cost of a normal VM. The downside is, of course, that the VM is guaranteed to be killed within 24 hours, and more often than not, it's going to be killed earlier than that. So availability is the, so basically trade availability for cost. But fortunately, since we're running multiple copies, we can afford running some copies on preemptible VMs so that even though some of them are unavailable sometimes, overall, we still have a highly available database. And to run 2 copies, we don't have to pay twice the cost. So far, I've talked about how we build this framework called SmyteDB using just a few off-the-shelf components. An important point here that Smyte is a security shop, not a database shop. So we don't want to reinvent any of the distributed system primitives. And in SmyteDB, we don't have to do any of that. We get all these nice properties from the frameworks that we applied, such as Kafka and Kubernetes. And on top of that framework, we can build our own counters database, for example, with just over 100 lines of code, which is also open source on the Smyte GitHub account. So there are other databases that we also build with the same framework. For example, we can build a general purpose key value storage using the same technique. Instead of increasing and decreasing accounts, we just do set and get with a database. Also, as I mentioned, there's a very efficient label database, which is really a list store with the same idea, but instead of doing point lookups, we can leverage RocksDB's ability to do very fast prefix scan for that. And yesterday, we actually wrote a blog post about a new similarity service that we built on top of the framework. And the idea is that we want to create a lot of queries that we can use to say, give me a list of users that's similar to this, or a list of images or text clusters that's similar to the question in the query, so that we can apply similar labels to them. So this looks nice. What can go wrong? Let me share just one story here. At some point, we were running our own Kubernetes cluster, and we did a minor version upgrade. Unfortunately, there's a risk condition in the new version and that actually wiped out all the disks in one zone. Unfortunately, we have replicas in different zones, so all we need to do is take a recent backup for those disks, and then just consume from Kafka. Within the hour, we get our second backup back without much trouble, and this process isn't that much different from, say, recovering from a MySQL replica. All right, that's all I got. Thank you for listening. Any questions? I use Google Cloud.
Are you still using S3 to back up the Kafka?
We're actually mostly using Google Cloud storage, but
You're still backing up the previous Kafka?
a selected subset. Since we're doing writes to the persistent disks, right, we don't have to do that. We just need to take a snapshot. But for the certain things that are more critical, we do that separately so that we have higher guarantee. Yes? So you're asking about latency. I missed the second part. For what? Yes. Yeah, all kinds of user activities. Yeah, so that's right. So yeah, that's a very good question. So there's the read part and the write part, right? So once the data gets into the database, the read latency is actually pretty low. Thanks for Kafka and the persistent disk. Usually it's in like 90 percentiles in order of tens of milliseconds, if not 100 milliseconds. But the write part can be slow, and actually the latency depends on how we configure our Kafka producer and consumers. So the latency can, depending on application and the configuration, can range from say 50 milliseconds to a second. As I explained earlier, for most of our applications, that kind of latency isn't the end of the world, because there's a latency between when customers send us data and when we can get the data into our system. So having extra, say, 500 milliseconds of latency is not going to reduce the quality of our classification by a large extent. So we accept that latency, and we buy instead a lot of throughput and ease of operation by using this approach. All right, cool. Thank you.